Okay, everyone, welcome to our third TAMIDS Scientific Machine Learning Laboratory seminar. And today we are very, very happy to get Sanjay Choudhry. I hope I pronounced your last name right. So Sanjay has been in this scientific computing and the engineering field for almost several decades, right? So the first time I saw your name was probably when I was still a graduate student, working on some portal. I'm not sure you're familiar with your work still at the ESI. You're working on very nice real-time sharing environments. That's exactly something we were trying to do.
Oh, C-Space. Yeah.
Yes, it's amazing work, you know. And we were working on a project trying to get the users supported to run some simulations on our big systems. We call it science sketchway. In academia, but in industry, you call something different. There are different terms, but it's a wonderful work. And that's the time when I first heard your name. And then after a couple of years, when I started working on machine learning and all the other computational stuff, and I heard that Sanjay moved to Nvidia, and he's leading the team doing scientific machine learning over there. And that's exactly something we have been talking about here at Scientific Machine Learning Laboratory, the PINs, physics-informed neural networks. That's exactly what Simnet is about. So today, Sanjay will be giving us a presentation about his work on scientific machine learning, and also especially the Simnet. And with all that said, I'll give you the microphone. Let's welcome Sanjay.
Oh, thank you, Jian. I appreciate your introduction. Yeah, so hi, everyone. I'm Sanjay Choudhry. So I started my career basically doing commercial software development. So mark analysis, from which Abacus came out from, basically the first nonlinear finite element code. Mark originally started at Brown University. That's where we did all the nonlinear finite elements, basically large strain plasticity or different kind of material models, etc. And then I led the product development and product management at MSC Software, which makes NASA and Atom, Patra, and all the other visualization tools, basically. And then, as Jian actually interestingly recalled, yes, I did a startup. It was a venture-funded startup called C-Space. My co-founder was a professor. He still is a professor at Carnegie Mellon, Professor Kenji Shimada. So we did the first cloud-based HPC platform, and I'm pretty proud of that work because there was no other such platform end-to-end that was available at that time, where you had client-side visualization for geometry meshing, you had server-side visualization for the large computational results, basically, and some of the clustering that was needed, which the cloud was not equipped in those days to do, but we did our own stuff. And then the company got acquired by ESI, where we did some of that, plus machine learning and AI. And here I am presenting to you about Nvidia Simnet, which is another innovative product, basically, that takes the simulation to the next generation. So this is how I would characterize AI and Simnet to be. So I've seen over the last 3-4 decades, basically the entire evolution of computational sciences and simulations, basically, and the algorithmic approaches and so on and so forth. And really, what the really freshness about this is, while the previous versions and approaches were evolutionary, this is what I would categorize as revolutionary, because it's a completely different type of work, basically, that aims to sort of take the simulations in the future, basically, into a completely different realm. And I'll be talking about that in the next few minutes. So I would like to acknowledge the team behind Simnet. And these are the folks who have done a lot of good work. Clearly these names are not the only names, but certainly the ones that are the most closely associated with Nvidia Simnet. Nvidia Simnet can be found at developer.nvidia.com/simnet. And anyone can register. Please don't forget to use your official email address when you register. And anyone can register and download the documentation, source code, manuals, examples, etc., whatever's there. So basically, there are different domains of scientific computing and simulations that exist today. And NVIDIA actually is in each one of them, because as you know, NVIDIA's evolved from a graphics to a supercomputing company to an AI company to now a compute platform, basically with a full stack, basically from hardware to applications. And so it's obviously involved in each of these, both from a numerical simulation point of view, improving their performance on the GPUs, but also recently in the last few years on the AI side as well. And there are different areas or groups in NVIDIA who are doing substantial amount of work in different domains. I would be talking about, and we are concerned primarily about the first one, which is basically the computational engineering, digital design, manufacturing, and adjacent areas. The earth sciences and life sciences will be, I would say, adjacent areas, but typically these are the areas that we are involved in.
Sanjay, do you want to maximize your window?
Yeah, so the only issue is, Gian, if I do maximize that, some of these slides are recorded and they'll start playing actually, which is not something we want. But if you have any difficulty in seeing this, then,
no, I think it's okay. Thank you.
Yeah, okay. So as I was mentioning, actually, the simulations have evolved, and really the first generation took the physical prototyping to the virtual world, and that was basically using traditional simulations, which is still basically the workhorse in the last few decades, which typical finite element, finite volume, finite difference, lattice Boltzmann, boundary elements, you name it, right? I mean, those are just all different types of numerical methods and schemes, basically to address the partial differential equations, ordinary differential equations, etc. And then recently, AI-based techniques for simulation, and this is where I think we believe the future is going to go, for the simple reason that not only do they have the ability to address what the traditional simulations can address, but they can also address a lot more that the traditional simulations today cannot address and will never address, just because of the limitations that are inherently there. And that's what makes it so exciting to see that there's something that can cover the gaps or paint the white space that exists because of the traditional simulations. The AI, basically application simulations today is mainly in two different forms, what I would call a data-driven form and a physics-driven form. And one can actually, even physics-driven has a whole range, basically, of what physics-driven means, right from the point of view of correcting the inferencing mechanism that's already learned from data-driven to doing the full simulations all the way from A to Z. And in the data-driven basically form, which most of you are very well familiar with, is basically taking essentially lots and lots of data that has been produced somewhere else. Doesn't have to be simulation data. It could be simulation data, but it could be measured data, experimental data, all of those. And you have neural networks basically learn the behavior, essentially. And this is something that has been the most dominant sort of way of doing things until very recently. And things are changing now because people who are in computational domain, they don't necessarily trust the pure data-driven approach as much, just because no one knows exactly how good those predictions are and how well they're obeying the partial differential equations. And so some of these new techniques that have come out involve modeling it fully, basically like a traditional solver would do, except that these are neural networks. And in that sense, you can add one more name to the list of names that I had mentioned before, in terms of numerical methods. So in that sense, it's another numerical method, but it's a very powerful one in the sense that it is able to fill the gaps, basically, that some of those original numerical methods were not able to. And it has its own issues right now to deal with as well. But considering that neural networks today are where finite elements were in 70s and 80s, it requires, it'll require some development, both in terms of architecture of the networks, algorithms, and other things, performance basically. And of course, performance is going to be taken care of partly by invention of newer systems as well as GPUs, but even otherwise, the features that are needed for such kind of simulations. And those are the kind of things that are active areas of research, both in the universities as well as in the industry. And these are exciting times. So from that point of view, we do recognize that while we are at the forefront of these kind of methods and simulations, clearly there's got to be, nothing can be done by a single organization or an entity. And it would be a good idea for us to all collaborate on a platform, basically, that we can share and develop, basically, so that people don't have to reinvent the wheel. Because this is one of the things that I'm seeing, that there are lots of islands of excellence throughout the world, where work in this area, novel methods are being developed, techniques are being developed, networks are being developed. But they unfortunately are not pursued, in a way that I think they deserve in terms of looking at by different other groups which are doing the development. And so some of the reinvention of the wheel happens, and those are the kind of things we are hoping will probably minimize using Simnet. Nvidia has basically has its weight behind Simnet, and that is one of the things that I was talking about in terms of the software hardware stack. So just to mention, I don't know what the background of this students and other researchers and faculty in this webinar is. So I just chose to kind of explain a little bit about what the data-driven methods basically typically today are. And that involves, training on certain objects or certain types of geometries, basically, and then creating a model that can be verified with some more real-world type of use cases, and then in inference, more of those, basically. So essentially, it's learning from the data. And here, it's a very simple 2D automotive aerodynamics problem where we took several primitives, different shapes and their combinations, and we trained the flow on those primitives for the velocities and pressures and so on and so forth. And then we did the verification on some other shapes, both primitives as well as real car shapes. And then with the inferencing, you could actually then do aerodynamics on these cars of different shapes, essentially. you will get the pressure differences and velocity differences, and you can see they're fairly reasonably close within up to certain error tolerance, basically. But the problem is that while these are not dependent on physics, which basically I list as pro only because there are many types of physics, many types of phenomena today where the physics is not very well known. I'll give you an example where I was talking to one of the major car companies, and they were trying to study the process of window defogging. And the best commercial code basically that they could use for CFD in this case was giving them 50 to 100% off answers off basically. And they were very, very happy with. Usually it was 3 times and 5 times. So there are lots of phenomena where the physics is not either well established or not yet sort of defined for some of those things. And where the data-driven networks actually can do a reasonable job if you have a lot of measurements and experiments basically that have been conducted and you have the real data available. But in general, there are lots of limitations for such methods, and there is no physics awareness. That's clearly, at least in the very pure form of data-driven network. And so the generalization ability generally is low. Also, if you really want to solve something complex, then you need lots and lots of different simulations, which may then again be dependent on the accuracy of the simulation code. And not only accuracy, I would go as far as to say the expertise of the user, because you can actually end up choosing different schemes and different parameters, and you can have 2 different users use the same code and get 2 different answers, or the same user using 2 different schemes in the same code and get 2 different answers. So there are a lot of variability that exists basically. And so these simulations basically that the neural network is learning happily are basically limited by those things themselves. They are obviously going to be difficult when it comes to complex geometries and curved surfaces, although some of the graph-based neural networks are attempting to address those issues. And then finally, the interpolation, extrapolation errors, which can happen when learning these solutions or really predicting these solutions, have their own issues as well. So with all that, basically, what is SimNet? So SimNet is a purely physics-driven, basically neural network, which can be applied to any general, ordinary, or partial differential equations. And typical area of application here is in engineering physics. Basically, although one can say that the same process can be applied in other areas of science and even business for that matter. We have implementations in SimNet both in the differential as well as integral forms, the variational form that is, which brings us closer to some of the existing numerical schemes that are there. You can also do reasonably complex, moderate complex geometry simulations, which most neural networks are unable to do because we have a great library, which is also developed at Nvidia, where we can do point clouds on STL files and some of the complex geometries. We have our own the constructive solid geometry module, which we can use for parameterizations, etc. There are multiple network architectures and features that have been developed in SimNet, and these can be parameterized for both physics as well as geometries. And of course, no discussion at NVIDIA is ever complete without discussion of performance, where we have done a lot of work, both for single GPU as well as multiple GPUs and nodes. And I'll come to that in one of the slides later on, where if you adopt SimNet as a platform to do your own research and do your own development, then you get all these things that you don't have to necessarily worry about, both in terms of performance, in terms of physics, in terms of geometry. and more importantly, in terms of APIs, examples, and manuals. Most of these kind of products basically are codes that exist, or libraries that exist. Basically, they have maybe some publications behind them, but generally, the focus in the universities is different. Obviously, more on research, and so clearly, it's not in the same developed with the same intention, basically, which we are doing, and which is basically to be able to serve as many users and developers and researchers as possible. And the scope goes from the universities all the way to the industries. So complex algorithms to complex physical problems, basically. And the 4 areas basically of Simnet development that we have undertaken, which will continue in perpetuity, are, one is the physics, where you're solving different kind of problems, whether there are forward problems, starting from a problem description going to the end, which traditional solvers also do, or inverse problems, basically, which require some sort of data at the end, and then traditional solvers cannot do that, or data simulation where you have some data and some physics, and basically you're trying to predict all of that. The parameterized geometry, basically ability to do that both for physics and geometry, to be able to do multiple configurations simultaneously. And this is really where the neural networks shine, because it's not the single case, basically, where they can really beat these numerical solvers, which have been really fine-tuned for performance. Then the performance itself, is going to keep continuing, because it's clearly one of the things that we want to make sure that it runs as fast as possible. And then we are also keeping in mind all the developers' needs, users' needs, in terms of implementation. And so we give complete freedom. That's why the source code is available, so that you can modify the code, and you have examples to work off and look at, basically, if you want to sort of learn the code quickly enough, then that is something that can be done. So it's a very, there are nice tutorials and examples to get you started, basically, with these kind of approaches. As I said before, the code and the package is available at developer.nvidia.com/simnet. This is available both in a bare metal form for power users, as well as in the container form for beginners, basically, so that people can get started quickly. They can solve the examples and do their own modifications, which may not be very extensive to begin with. As you can see, the architecture itself is very modular in nature, and basically can be changed. The current algorithms implementations can be changed based on what you want to implement for yourself, for your research. Then regarding the architecture and features, I will not go into any detail on this one, because there's not enough time. And secondly, if you download the package, then in the user guide, chapter 1 is devoted to theory, and all these are described there. Some of them are actually our own creations, and some of them are modifications of what exists in literature. But nevertheless, you can see that, anyone who has done simulations, basically, in scientific problems, knows there are singularities, there are discontinuities, there are gradients in the solution, introduced partly because of either the nature of the physics or nature of the geometries, and all those complexities impose a very exacting requirement, basically, on these kind of simulations and these kind of tools. And so a lot of these have been kind of developed and modified to address those difficulties, basically. And of course, we always, we have tried different physics types, And we always verify against either open source or commercially available solvers. So, for each physics type, we take the basic simple problem, verify that, and then even complex ones, we verify that. So everything that I'll show you today will also have a comparison with something that exists, so that we establish the confidence and trust in the approach going forward. So in CFD, the simplest example is, of course, the 2D lid-driven cavity, for which we got fairly decent comparisons, open foam. For solid mechanics, this is a bracket deformation, and for which we got a very good comparison with MATLAB. For acoustics, basically, it's just a comparison between the different schemes that are there in neural network with continuous time, RNN and GRU. And GRU is turns out better than RNN for longer time periods and continuous time period. So in this slide, you can see the different areas and domains where Simnet has been applied. The first one is improved physics and predictions. Here, actually, neural networks can be on their own, or they can work in conjunction with a solver. And on their own, of course, you can do a lot of, learn from the data and do the simulations, but they can also be embedded and called by the solver, because typically the solvers, like for example, whether it's RANs versus LES or DNS or micromechanical material model versus the macromechanical constitutive models, where you have a gross behavior modeling of stress strain or something like that, as opposed to unit cell behavior and composites. Those kind of things can be well learned by neural networks and be called by traditional codes, so that you have the best of both worlds. You have the accuracy as well as the speed that's needed, because otherwise, typically, even the largest of the computers today that exist, are not enough for people to be able to do this on a regular basis. You might see some challenge problems here and there, but not on a regular basis. The inverse and data simulation problem basically are totally, so on the right-hand side is actually the domains where you have traditional solvers, but speed is a big limitation. On the left-hand side, the traditional solvers don't exist. And on the y-axis, basically, you have single simulations that are typically done in these domains versus multiple simulations that are done. So coming to the inverse and data simulation problems, whether you have FWI, full wave inversion using acoustics for oil and gas, where you're trying to detect the oil and gas deposits or different kind of deposits in the ground, and based on the signature of the wave at the seismometer, basically you can figure out exactly what exists under the ground, or whether it's medical imaging where you have the flow field visualization, but from that you calculate the actual velocities and pressures, etc., to calculate the wall stresses, etc., or climate, whatever they are, these problems they have some data that is measured data. And then if you fuse that with the physics, then you get a very good sense of the rest of the field for that problem. This is completely a new area that has now come up, because most of the time the traditional simulations don't address these, or if they do, then there'll be a repetitive back and forth iterative manner, basically, where you're kind of essentially doing with a problem with a guess, And if the answers don't match, then you change something in the boundary condition or material properties or something, and then rerun the problem, which is extremely inefficient way of doing it. And real-time simulations are the biggest sort of, bang for the neural network, where whether you have digital twin or robotics or autonomous driving, you have instant decision required based on certain data coming in. And neural network have the ability to do that, whereas the traditional simulations, one can't even think of applying in these kind of areas. Reduced order methods basically have come up, but I don't particularly like them, because they are very specific, problem specific. Nonlinearity is an issue, and really not as flexible as neural networks basically. So that, I think, is poor man's approximation, but nevertheless, I think we have the ability with the current hardware and software to do better than that. Digital design and manufacturing, of course, this is something that any industry which is making any kind of product, whether it's automotive or medical or electronics, they go through in terms of product design, which involves the different kind of physics. And now I'll show you some of the examples for each of these domains that was done. They were done by Simnet. So with the improved physics and predictions, basically, the first problem is a 2D seismic wave problem, where essentially we have a single Riker wavelet source, and we solve this problem using constant and layered velocity models. Basically, for the constant velocity model, you can see that the comparison with a finite difference code, DeVito, that exists on the GitHub for small times basically is excellent, and it continues to be that way. But there is slight reflection shown by the finite difference code, which should not exist because the boundary conditions are not reflective. And so here the Simnet models it correctly, basically, and that becomes a lot more accentuated when you go to layered velocity, where it's for small times, it doesn't do it, but for moderate and large times, there's a gross reflection taking place with DeVito, which did not take place with Simnet. So this is an area where the neural network actually ended up predicting it better than the traditional finite difference case. This is an example that was done by Cedric Fressis. He's in the Energy Resources Department at Stanford University. Using Simnet, he was able to capture the front very accurately, as you can imagine. These are typically done by using method of characteristics for the true solutions, solving a flow in a porous media using a Buckley-Levert equation. This is hyperbolic in nature. And this kind of front is very difficult to capture. Typically, the commercial finite element code or numerical methods can do it, but there's a little bit of chance involved or luck involved in doing that. And the luck is that they use meshing or some sort of domain discretization, and that introduces diffusion in the solution. And that diffusion makes this problem parabolic, which then becomes easily solvable and not a pure hyperbolic problem. And so from that point of view, I would say Simnet actually does a better job in terms of keeping the problem pure. The next domain is inverse and data assimilation problems, where for the inverse problem, you have the result and you're basically trying to find something from the initial state. In this case, we took a conjugate heat transfer, 2D heat transfer problem. The temperature field, flow field is known, and you're solving basically the advection diffusion equation with the boundary conditions or interface conditions of equal temperatures and equal fluxes at the interfaces. And we got the coefficients, which basically, so we did the solution with OpenFOAM, but in OpenFOAM, that was the input, and we got the result and used the OpenFOAM result with Simnet to predict the coefficients back, which are very, very close in terms of kinematic viscosity and thermal diffusivity. So with that, we show that Simnet is able to capture these coefficients very well and is able to solve this inverse problem correctly. This is a problem that I was actually originally mentioning early on, that the users basically, when you are using data-driven methods, the code will learn, or the network will learn the fidelity of the solution that you will show it. And here, this is a flow over the cylinder problem. And if you notice that the exact is the what we call open form solution. That's for the moment we say, okay, this is an exact solution, although we know it is not. And we are trying to learn that using Simnet. And you see a terrible comparison. And we thought originally maybe the problem was in the code or the way we modeled it. But it turned out that there was some user error. Actually, it wasn't even quite a user error. It was just a precision error, that one of the coefficients, basically a turbulent viscosity, was modeled as a non-zero quantity. And because of that, even though you don't see it in the finite volume result by OpenFOAM, you clearly end up seeing some garbage coming out in the neural network prediction. So when we fix that to exact zero, and we reran the solution as a true laminar case, basically, there was the comparisons were excellent, basically. So this is why we caution that there's a difficulty, or I shouldn't say difficulty, but there's a possibility of going wrong when using data-driven networks, basically. The second example is that of a medical imaging of an intracranial aneurysm. This geometry originally came from Harvard Medical School to Brown University, and from there it actually came to us. They had solved this as an inverse problem. We have solved both inverse and as well as the forward problem. So it's an STL file, and with our geometry module, you can create a point cloud for the STL module, basically with what we call Nvidia SDF library, using a race tabbing method, and then feed it to Simnet. And the results that we get basically are in good comparisons, basically, but you have to see that the Simnet ran this problem as inverse solution, but the traditional solvers do not solve inverse problems. So there we ran it as a forward problem. With OpenFOAM, the results are good, except at the most important location, which is where the bending stresses are the highest. And we went to Nectar++, which is a spectral element-based higher order scheme, and that gives us much better comparison, basically. And this kind of shows that solvers also can disagree and give different results, which basically means that you cannot call solver a ground truth either. And in fact, in most of these cases that I've shown so far, actually neural networks have done a better prediction than the solvers. So in many cases, we have seen you have to refine the mesh to come to the same kind of fidelity, basically, with the solvers. And also, depending on what kind of schemes you've used, whether first order, second order, etc., that can make a difference as well. This is a solution using forward this thing, and this is a very difficult problem actually for the neural networks to solve as a forward problem. That's why many of the problems that you see that exist out in literature using pins, physics-informed neural networks, basically are solved as inverse problems or data assimilation problems. And so where you have some data available, no data was given, only the problem description, and we got excellent results basically in velocity and pressure comparison with OpenFOAM. The geometry is not difficult, but difficult enough for a typical neural network that unless you use some of the schemes that we have developed, which are SDF-based loss weighting and continuity integral planes, etc., you will not get a good solution for this problem. You may not even get a solution for this problem. So that's where Simnet actually has some of the innovations that are helping to solve the problem. The next area is real-time on-demand simulation. And this is an example of a digital twin. And this was done using a Simnet by the University of Central Florida, Professor Philippi and his group, who applied this to make an RNN for where Simnet was used as a physics node for the damage accumulation in an aircraft panel, basically. And this is a problem that has been well described in a video that exists on this, which I can send to you in my presentation after this. And they were using Abacus before, using Simnet. And in Abacus, when we compared the result for the aircraft panel, results came out to be very different. And we thought, what could be the issue? And we started refining the mesh in Abacus, and they converged to Simnet results. So all the results, again, one of these, they point out that neural networks have the ability to solve the equation in the strong form and without discretization, which actually with enough number of points in the cloud, basically, you can end up getting a very good fidelity of the solution. And the final area is the digital design and manufacturing, where we take a very complex geometry of the heat sink. And I say complex because these are fins which are very thinly spaced apart. It's a turbulent flow, and it's very difficult for the flow to develop, basically, in this very complex geometry with the heat pipes and everything. And we use that, we used ANSYS IcePack to do the simulation, and we used Simnet, and we got very, very good results, close results. Actually closer with the commercial solver than with OpenFOAM. We found OpenFOAM is not as mature or good, even after so much use, as some of these robust commercial solvers over and over with the last few problems that I've shown you. And but we got reasonably good comparisons within 10% engineering accuracy with a commercial solver for both temperature and pressure drops for this heat sink. And this is fine. This is a NVSwitch heat sink that goes in at currently out in the market, DGX A100. So for one geometry, you can get good simulations from these traditional solvers. But when it comes to multiple design parameters, the traditional solvers they fall way short. And here is a 10 parameter problem. We took 3 values per parameter, so the 2 extreme values and 1 in the middle. So immediately the problem becomes 3 to the power 10. And Simnet actually takes 1000 V100 GPUs, whereas the traditional solvers, we didn't even, we calculated how much time it takes for one solution, and for these many runs, it will take these many times, which is just theoretical actually. And even if you do 1,000 fewer simulations, it will still be intractable amount of time, basically, which traditional solvers will not give you the luxury to do. And this is where I think the main, besides of course real time, this is one of the big things that the neural networks can do. And finally, my last slide is on performance. Basically, we did a lot of work on that. As you can see, for the single GPU case, going from V100 to A100 without any modifications for a problem, we got 50% speed up. Now, this is only for one problem. In some cases, we may get less. Some cases, we can get much more. And for going from a FP32 precision to a TensorFlow 32 precision, we get double again in terms of performance. And so going from a V100 to A100 with a TensorFlow 32, you get immediate 3x improvement in speed. And we did substantial studies both on V100 as well as A100 on weak scaling as well as strong scaling. So we kept on increasing the number of points with the number of GPUs, so larger and larger batch sizes. And that that would give us a better accuracy and convergence characteristic with larger batch sizes. But we were able to do that without actually increasing the time per iterations as the number of GPUs got added. If the workload remains constant, basically, and you increase the number of GPUs, you can get lesser and lesser time per iteration. We started running out of memory, basically, in some of these later stages. So it kind of became less than superlinear, but you can see otherwise it has good performance. XLA, actually accelerated linear algebra in TensorFlow, even reduces the time further. So with that, I would like to conclude my presentation. This is just the roadmap. We have a continuous release cycle with every somewhere between 3 to 5 months, depending on the features and use cases. As I said, our aim is to do both algorithmic work, introduce new architectures, but at the same time, do application work as well in terms of, to be able to solve complex end user problems so that we can sort of demonstrate the applicability of this field in the real world, so that at some point in time the world can truly take advantage of AI in scientific computing. So with that, I would like to thank you for your attention, and I conclude my presentation with that.
Thank you very much, Sanjay. Any questions? If you have any questions, feel free to unmute yourself and ask directly.
Hi, I am Arun Srinivasa, and I had a question. Are there any limitations, or have you solved all the physics and engineering problems that there are?
No,
because it looks like you're basically saying you can solve anything.
No, actually.
So because you didn't mention any limitations so far.
Yeah. There are so many limitations that if I would have started mentioning the limitations, my presentation would have just been full of limitations rather than anything concrete that we have done. Clearly, this is a very, very scratch the surface work. We are learning a lot in this field ourselves. There are very few, basically, even with all the literature that exists and all the work that's going out in the universities today, there are very few relative number of publications that are there in this field compared to the traditional numerical methods that exist. This is just to show the promise of the neural networks and what can happen, what can be done, basically, rather than really saying that it can address anything.
Yeah, but is there any particular big item that you really think, okay, this is something that cannot be done either this way or any other way or something like that?
Well, I think okay, let me give you one limitation that we are trying to solve ourselves, and this is a very concrete example. It's at the low level in the sense that it's a very small item, but there are lots and lots of these small items which add together to make other bigger issues. And the particular issue here is if you apply Naumann boundary conditions, for example, in neural networks, where in cases where the gradients are changing very quickly, that can lead to convergence problems. Now, whether you solve it by introducing a better neural network architecture, or whether you solve it algorithmically, is dependent on which side of the domain you come from, whether you're a computer scientist or whether you are a mechanical engineer. So where does that, for example, apply? In the conjugate heat transfer problem that I was showing for the heat sinks, you have that kind of boundary condition where you're matching the fluxes. And those fluxes basically are in the fluid, the conductivity is very small compared to the conductivity of the solid. And so there's a huge mismatch created at the boundary, and the gradients are there, because of which essentially we solve the problem by introducing a different uncoupled algorithm, but one could envision developing a better neural network. For example, the neural networks previously were, originally were using fully fully connected networks, and they still form workhorse to be the workhorse in many cases. And that solves certain flow type of problems. But the kind of complex flows that we have solved, actually, we saw those to be pretty, not be working. They go to a certain extent with some of the techniques that we have developed using the loss weighting with sign distance functions, as well as the integral continuity planes, basically. But even for complex geometries, those are not enough. So we went to some modified form of Fourier networks, basically, that we took from the literature and then modified it for our needs, basically. And so I think the point I'm trying to make is work will have to be done at both, on both ends, the physics side of it and the neural network side of it, basically, to solve these kind of problems, which might not look difficult, but when you start solving real world problems, they jump up. I could always solve a conjugate heat transfer problem where I could easily fake out some of the coefficients so that they have only a multiple of 2 or multiple of 3 for the sake of just solving the problem and solve it the way it is to be solved. But that is not, unfortunately, the real world. And that's why I was saying that this, with Simnet, we intend to be a real world problem solving platform as well. And that's where I think some of the research work is necessary in terms of being able to do what the neural networks today are not being able to do.
Sanjay, I have a question. My name is Raktin Bhattacharya. I'm with the Aerospace Engineering Department. I work in computational techniques, and then mostly our focus is on uncertainty quantification. So looking at the results that you've shown, I mean, by the way, they're excellent, and it's just amazing what Nvidia has done, and then the scientific community in general in this space. One question that I have, that most of the results that I've seen, in your presentations and also from other researchers from Sandia, is there's always a reference which is used to assess the quality of what the neural network-based solution is giving you. When do you think that we can assess the accuracy and the correctness of the neural network solution without showing any of these baseline results? And that's kind of related to uncertainty quantification, that how would I quantify the errors directly from this neural network architecture, and then what would be a methodical way to kind of refine the system so that the error is reduced? Some sort of, I'm kind of looking for a consistency of approximation here. Any thoughts on that?
Yeah, that's an excellent question. Actually, we are working on this ourselves. And in fact, if you look at the roadmap, uncertainty quantification is on the roadmap. So we are working on it. But that's exactly coming back to your point of, why do we show the reference? I think all the people who have had any background in computational sciences and especially coming from the side of the commercial software development, basically, there's always this, element of doubt with any newfangled method, that exists, that are these just a fad, or are these really truly, going to, change the mankind in terms of, their approach, new approach, basically, that they bring to the table, essentially. And I think most of these comparisons that you see are just to kind of calm down the hard sort of background mechanicians, basically, I would say, who are going to be sort of very skeptical of these kind of things. Just like in olden times, people used to be skeptical of finite element solutions, people who used to be used to analytical solutions, for example, using the, PDEs and the closed form solutions, I should say. So coming back to the uncertainty quantification, I think that's also a work in progress. Many universities are doing some very good work. I don't want to name because I'm afraid there are people out in this audience who are doing work and I may not sort of know about, but that's they are still algorithmic. And so how does one, even if one comes up with some sort of a good methodology, basically in that regard, there will still have to be that same comparison, whether you do it based on probabilistic methods or whether you do it based on measured data. But I think reference in the beginning will still be there for those methods too, until one can reliably prove that that uncertainty quantification is the correct uncertainty quantification, basically.
Thank you. I think that's good enough. I think it's an open-ended effort right now, and then since it's something that you guys are working on, I think it's exciting to see that it's on your roadmap. Thanks for your answer.
And we would be happy to work with other people in the audience who might have better idea than us, better ideas than us, because at the end of the day, we recognize that this is something that we will definitely need as many sharp minds as possible.
Sure, I think we've got some great researchers, and then we have an initiative here in Texas A&M that is kind of looking at this side of the story as well. Many of us are in the audience right now. So yeah, I think this is exciting. Thank you.
Okay, thank you.
Hi, this is Jean Dragusa. I'm in the nuclear engineering department, and we often solve Boltzmann kinetic equations, and basically the solution lives in a much higher dimensional space, typically 6 dimension instead of 3D for most of the simulations. Is it possible to use Simnet to do 6D simulation instead of doing 3D simulation? Do you see any roadblocks to increasing the number of the phase space dimensionality, for example?
I don't think so, because I know there's a researcher who's using Simnet at University of Pisa in Italy, who has gone for astrophysics, and he's gone to like 1,000 dimensions. So I think that we have not done it ourselves, but I know people who are doing it.
Excellent, thank you.
Any other questions? So I have one question, Sanjay. I don't remember you ever mentioned about the IP and other issues. Assuming someone from the audience might be interested in collaborating with you guys, what are the restrictions? Are there any hard constraints that we need to follow, things like those?
Okay, that's a great question as well. So it goes both ways, about NVIDIA IP as well as the university IP or your personal IP. So as far as the NVIDIA IP is concerned, basically, anyone who uses Simnet is free to use for research, modify it, extend it. The only thing right now, the current EULA, the end user agreement, prohibits basically is commercial use of that. However, even that, actually, we are working on having a separate licensing. Separate licensing doesn't mean cost, but separate licensing simply means ability to bypass the original licensing, so that in case you want to distribute it further, for example, for whatever purposes, to your partners or anything else, basically, then that could be done as well. And especially for the university, there's no cost, obviously. Regarding the other way around, which is, what if a researcher, whether a student, a postdoc, a professor who develops at the university and then wants to sort of integrate that in NVIDIA Simnet, then what happens? So in that case, your IP remains your IP. You will have to give us a license to use it, integrate in Simnet and use it, but it remains to be your IP. In case someone else wants to do something with it, they can deal with you directly in terms of the royalties or whatever you might want. But that's the way we are going to handle that, so that your IP is protected in that sense. If you would like to have it be in the generally releasable, publicly released code, basically.
Okay, let's see. Anyone else? Okay, if we don't have other questions, let's just call it a day. And let's thank Sanjay again for his wonderful talk. And hopefully we can work with Nvidia in some future projects. And thank you all for joining us. See you all next time.
Jintao, thank you very much for hosting this event for NVIDIA. We really appreciate it.
Thank you so
Sanjay,
much.
thank you for your time as well.
Thank you.
Everyone,
Thank you very
thank
much.
you.
Thank you, everyone. Take care. Bye-bye.
Bye-bye.
So Rianta, when do you think we can play with this in our HPC system?
That's a good question for me. Actually, I tried it already on Grace. It's working.
Oh, it's installed?
No, it's not it's not on a system level, but I installed it on myself.
Okay.
But I talk with folks at HPLC to see if we can get it installed on a system level. I'll see how that will work.
Okay, thank you so much.
Sure.
Yeah. So actually, to use Simnet, we need to agree to the user conditions on NVIDIA. But once we have this, we can download it and use it. But would it not be easier that there's a module that is in common for everyone, rather than everybody trying to install it on Grace?
Okay, so can I answer that question?
Sure, go ahead.
Okay. So yeah, I'm still around. If you don't want me to,
Sorry.
I can drop off. But I kind of wasn't sure whether I was supposed to be or not. But I'll answer this question. So what NVIDIA requires is for each user who wants to use it to register on the website. But that does not mean that they have to have a separate copy of their own. So you could have one system basically be installed on a university system, basically one instance of Simnet that could be used by everyone, or you could collaboratively develop and do whatever you would like to do with it. But as far as the users are concerned, we would like to individually have the names on the NVIDIA registration. And there's a good reason to do that, because this is a fresh, new fledgling product. We are trying to do, see who's using for what, and it helps in product management, it helps in feature development, and it helps in actually collaborative work as well. So I think from that point of view, we would require the user to register, but you can simply register and use Jiantao's version for that matter.
So one thing we can do, we can have a system installation and then just post a message every time you load the module. It will ask you to go there. If you registered, you can probably turn it off. Otherwise, we'll just keep showing the message. So just you go there and register your account on NVIDIA website. And we can
work.
Yeah. Okay, I think we call it a day again.
All right, great. Thank you very much.
Thank you.
Thank you, Sanjay. Take care. Bye.
Thank you.
Sure. Bye-bye.
Thank you. Bye-bye.